today. So anyway, so we will start our fifth lecture on graph theory. So I should share my screen first. Okay. So can you see the screen?
Yes, sir.
Okay. So this is the graph coloring. So first I write a definition. What is a proper K coloring? Okay. So what do you mean by proper K coloring? So first I take one example. So let this is a graph. Okay. Graph with 4 vertices. Okay. So proper K coloring means, or you can say that proper coloring. That's mean we need to color the vertices in such a way that no adjacent vertices have same color. So that's mean if you take say color red to here, then you cannot choose color red to this. So you need to choose a different color. So you give green to there. Okay. Now since now this vertex joined with red and green, so it should be a different color. Say this is blue. Okay, so we have three different color. And now for this vertex, see this vertex, we cannot choose red, we cannot choose blue, but we can choose green, right? Or you can choose any other color as well. So you can choose either green or you can choose any other color, say this one. Okay. So if you choose green, then it will be three coloring, proper three coloring. And if you choose this orange, then it will be proper four coloring. Okay, so this is the actually the definition of proper K coloring. So here K equal to 3 or 4. So formally we will write in this way. So let S be a color set of K colors. Okay. Now the graph G, which is the order pair V and E, has K proper coloring. So if there is a function f from the vertex set V to the color set S, okay, such that for any edge UV belongs to E, if U is not equal to FV. Okay, that's mean any two adjacent vertices have different colors. Okay, so this is called proper K coloring. Now we will define the chromatic number. So the chromatic number it is denoted by that chi G. Okay, so of a graph G is the list K for which G is K colorable. Okay, and a graph G is just we say K chromatic. If chi G equal to K. Okay. Now just read the definition. That's mean we need a list K such that it is a K colorable. Okay. Now can you tell me for this graph, what is the chromatic number for this graph?
2.
2. Why this 2?
We can just make a bipartite graph from this graph. So,
Right.
so we can say that we need only two colors.
Okay, so you can choose a by. So can you tell me the color with, can you give me a coloring with two colors? Say this is V1, this is V2, this is V3, this is V4.
V1 and V3 red and V2, V4 blue or green.
So you are saying, okay, I can draw. Okay, just a minute.
Oh, okay. Sorry. It's wrong. I didn't notice V1, V3. Well, I didn't
Okay.
take. Okay.
So if you choose V1, V2 red, it is not possible. V1, V3, it is no red. It is not possible, right? Because they
Right,
have
right.
an one edge. So what will be the chromatic number then?
Uh, then it should be 3.
Yeah, it is 3.
Ah,
Because we have already give the coloring with 3 colors, right?
yes.
So chromatic number is 3. Though it is 4 colorable as well. So this graph is not 2 colorable, but this graph is 3 colorable. This graph is 4 colorable as well. Okay. So since 3 is the least number, so that with that we can color this graph. So therefore the chromatic number is 3. Okay. Now we define click. So a click in G is a subset of vertices of G such that any two distinct vertices in the clique or in the subset are adjacent. Okay, and the the size of the largest clique in G is denoted by omega G. Okay, so clique means it is a subset of vertices such that if you choose any two vertices from that subset, they must be adjacent. Okay, now for this graph, can you give me one clique?
V1, V2, V3.
Right. And is this the largest clique? So what will be the omega G in this case?
3.
Yeah, omega G will be 3, right? Anyway, you can choose only V1, V2 as well. You can choose V1, V4 as well, right? If you choose the set V1, V2, that is also a clique. If you choose V1, V3 or V1, V4, that is also a clique. If you choose V1, V3, V4, that is also a clique. Right? So if you choose V1, V2, V3, that is also a clique. But if you choose V1, V2, V4, that is not a clique because V2 and V4, right? are not adjacent. So therefore it has two click of with three vertices, right? So therefore the omega g here it is 3. And later we will see that it is a exercise and it is a trivial one. It's trivial observation that omega g is less than equal to chromatic number of g. It is a trivial observation. You can see why it is true. And this is true in here as well, right? Here omega g equal to 3 and chromatic number is equal to 3 as well. That is a trivial observation. Now we have a theorem. For any graph G, chromatic number of G is less than equal to that delta G plus 1. So do you remember what is the definition of this capital delta G? Do you remember the definition of that?
So maximum degree of our.
Yeah, maximum degree of the vertices of the graph G, right? Now we will prove this. That proof is very simple. Okay, so this is a trick and you have to remember the trick because there will be many problem even in the tutorial sheet where you need to follow this kind of trick. So here is the proof and we will prove by induction. So we prove by induction. Okay, or induction on the, we can say that number of vertices. Vertices say n. Okay. So for n equal to 1, what is G? G is just K1. That is, it is just a singleton vertices. And here, what is your degree of G? It is a, what is that? If your K n is just 1,
0.
that is 0. And what is chi of G?
1.
That is 1. Right? So therefore, you can easily check that here chi of G is less than equal to delta G plus 1. Okay. So therefore, the result is true for n equal to 1. It's true for n equal to 1. Fine. Now, so since we will prove by induction, so we assume that the result is true for all graphs with n minus 1 vertices. So that is chi of h less than equal to delta h plus 1 if that vertex set of h is n minus 1. Okay, fine. But we need to prove it is for G of the graph G where the number of vertices is n. Now here vertex set of G equal to n. Okay, so what we will do now, let V be a vertex of G. Okay. Now take H equal to just G minus V. So you know, right, what is the definition of G minus V? We just remove the vertex V and the edges which are adjacent to V. So for an example, if I have this graph, say this is V. Okay. Now this is my G. So G minus V will be, okay, if I write this one, then there will be nothing. So better to write, okay, now we will choose not this V, this is V. Then it will be look good. So this is V. Then G minus V will be, remove this edge, this is and this vertex. So that will be this one. Okay. Right. Now for H, this theorem is true, right? So therefore, chi of G minus V less than equal to delta of G minus V plus 1. Okay. And we know that is also less than equal to delta G plus 1. Right? That is clear because that maximum degree of G minus V always less than equal to maximum degree of G. Okay. So that's when the chromatic number of G minus V is less than equal to this. Right? So therefore, we can color the vertices of G minus V with delta G plus 1 colors. Right? Now for an example, what was my delta G here in this case, in this graph? You look at the now example, this is my G. Now what was the delta G? That was the 3. Right?
Yes, sir.
Okay. And okay, so we actually this is 3 colorable. It is already 3 colorable, so therefore we do not need that. What shall I do for that? Acha, better to take. So actually this is 3 colorable. So I have taken, okay, anyway, this is fine. So, right. Now what we can do? I have already taken that example because this is already 3 colorable. Okay, anyway, it is fine. So with that example, you cannot visualize that. Okay, anyway, forget that example for a time being. So what we can do, we can just color that G minus V with this many colors, right? So in that case, that is 4. But here we can actually already give a coloring of 3 colors, right? So anyway, so we can color this with 4 colors, right? So that's mean take a arbitrary graph because for that graph that is a trivial one, so you cannot visualize that. Okay, so that is your V. say here delta G equal to say 4. Okay. And say remaining graph, that is my G minus V, and we have already 5 colors. 1, 2, 3, 4, 5. Okay. So we have G minus V. We can color it is by delta G plus 1, that is 5 colors. Okay. Now tell me how many vertices are there in this graph adjacent to V. How many vertices are there adjacent to V?
4. 4.
That is 4. That is the delta G. But we have
Sir,
taken 5 colors.
sir, I have one doubt. Means why are we taking this V to be the means is it possible that this V can be inside this graph G minus V also means there can be a vertex inside G minus V which has more which has more degree than this V.
No, you can choose any arbitrary vertex. So you start with a graph G and choose any arbitrary vertex V. That's all.
So sir, then how can we say that delta G is equal to 4? Means there can be a vertex inside it.
No. I'm just example. I'm taking one
Acha, acha.
example.
Okay.
That is just an example. So why I'm taking that example? I have taken this example, but that is trivial actually. So this is already 3 colorable. So since it is 3 colorable, so it is obviously 4 colorable, right? Because that graph already have 3 colors. There is no extra more vertices. So we need actually 4 colors. We need more colors, means at most 4 colors. Okay, anyways, so this is just an example. I'm taking that delta G equal to 4. Okay, I'm just taking that one. Okay, so what is V? Now forget about 4. Okay, if you want, you can just forget the example 4. So what we have, so V have delta G number of vertices adjacent, right? So there are here delta G number of vertices are there, which is adjacent to V. But we have delta G plus 1 colors. So that's mean there will be 1 color missed in this graph, in this vertices, which are adjacent to V, right? So G minus V has delta G plus 1 color and V is adjacent to at most, okay, delta G vertices. Even we don't know, it can be less than delta G, okay? So therefore, 1 color is missed in the neighbor of V, okay? So put that color for V. So we have a delta G plus 1 proper coloring for G. Is that clear? So what we'll do, we first take a graph G, okay, and choose any arbitrary vertex V, any arbitrary vertex. That does not depend on the degree of V, okay, so any arbitrary vertex. Now you remove vertex V. Now the remaining graph has 1 less vertices. So therefore by induction, that is delta G plus 1 colorable. Okay, so that's mean you can say that that can be colored with at most delta G plus 1 colors. Okay, now V has degree V has degree what? Delta G. But here we have delta G plus 1 colors. So therefore 1 colors must be mixed in the neighbor of delta, a neighbor of V, and put that color for V. So we have a delta G plus 1 proper coloring for G. So we are done. Yes. So any doubt or any comments? So is that clear? Then tell me, then so that I can go further. Or if you have any doubt,
Yes, sir.
you can ask. Okay, now there is a theorem that I will not prove. That proof is very long, but I suggest you should read from the book. So there is a theorem. It says that, so let G be a connected graph. Okay, so which is so neither complete nor an odd cycle. Okay, so then chi of G less than equal to delta G. So if you have a graph which is not complete or not an odd cycle, then chi G, that is chromatic number of G, is less than equal to degree of G, that is highest degree of G. Okay, so now this is the theorem. So I will not prove this theorem because this theorem is very long and it will be available in any book. So I suggest you just self read from any book. Okay, and remember the statement because you may need this statement to prove a problem. Okay. Now there is any one theorem. So every tree with n bigger equal to 2 vertices is 2 chromatic. Okay, so that's when if you choose any tree, okay, then you can color that tree by two colors. So you can choose any tree. Say this is a tree. Now, if you choose any tree, this theorem says it is true chromatic. That's mean you can always color this graph by two colors. Okay. Now, can you see the proof? So can you give me a quickly proof of this one? Anyone? It has one observation. Can you tell me? I am giving one statement. Can you prove it? So if you choose any vertex V, okay. Now if you choose any other vertex, say W, then V and W has unique path, unique shortest path.
Yes, sir. Because it's connected and acyclic graph. So a path would exist. So that part is done. And since it's acyclic, I mean, since there's no cycle and
Right,
like any vertex is connected to another adjacent vertex using one edge only. So there would exist a unique path only.
right. So if you write path, if you write walk, then you can say shortest one. If you write only path, because path has no repeated edge, then any two vertices have unique path, right? So the statement is any two vertices are connected by a unique path. Why? Because suppose there are two paths connecting V and W. Then if you take union of those two paths, then that will be a cycle. That is the proof, right? Why that is true? Because if you have two paths, say P V and W. So if you have two paths connecting V and W, then P union P dash is a cycle, which is a contradiction. So that's mean you always have a unique path. Now, since you have a unique path, now you can find the distance between V and W, since you have a unique path, right? Now what we can do, see, we first take color, say red here, okay? And whatever the vertex here joining with this, then we color green. Then again, whatever the vertex joining with red, green, we will write again red. So this is red, this is red. And whatever the vertex joining with red, you will put green. And do this. Red, 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 red. And here we have two green. So this is two colorable. So any tree can be colored with two vertices, with two colors. Okay, so what we'll do? So choose color 1 for V. Okay, now then put any color 1 to all vertices of T which has distance even from V. Okay, and give color 2 to all vertices of T which has distance odd from V. Okay, so since there are only unique path, so this even and odd, this can be determined uniquely because there are no other path, right? So therefore you can color T with exactly two vertices, and this is a with the two colors, and that is a proper coloring. Okay, so that is the proof of this theorem. That is very simple. Now by using this, we can prove another similar theorem. It says a graph is too chromatic if and only if it has no odd cycle. Okay, so that's mean a graph, in other words, you can say that a graph is too chromatic if and only if either it is tree or it has only odd even cycles. That's all. Okay. Now this theorem again, it is not a very difficult one. First, we assume that let G has no odd cycle. Okay. Now let T be a spanning tree. Spanning tree of G. Okay. Now by previous theorem, T is too colorable. Okay. So suppose this is G. Okay. So this is G and that black edges are the spanning tree. Okay. But we know that any spanning tree is too colorable. Okay. So that's mean you can color it is by two colors, say blue, green, 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 blue, 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 green, green. Okay. So first color T, right? T is too colorable, so we can put that coloring. Now if we give the extra edges E, so now add edges E. Okay. Now see, if you add one edge E, then you have a cycle. For an example, that black edges was a tree. Okay. Now if you put that red edge E, then you have a cycle. But that cycle is an even cycle. So therefore, that coloring, the previous coloring is fine for this. Did you get what I am saying? Because we know that any even cycle is also too colorable. Okay, so therefore that is fine. Now we can add the edges E with previous coloring, as it creates only even cycles and even cycle is too colorable or too chromatic. Is that fine? So what we are doing? So we need to prove if G has only even cycles, so then G is too colorable. So how to prove that? First we take a spanning tree, that is the black colored vertices edges. Okay. Now we know that any tree is too colorable, so put the two colors. Now if we add any extra edges, then that will create a cycle, but that cycle will be only even cycle. Now since those are even cycle and even cycle is always two colorable, so we do not need to add any extra color. The previous color is fine.
Sir, even cycle means
Even
number
cycle
of.
means it have only even number of edges, right? Since it creates an even cycle, so therefore the boundary of that edge E must have different colors, right? Because the distance between those vertices must be odd, so they have different colors. For an example, when you have E, this is your E. Now you can find the distance between this vertex and this vertex. So this is odd, right? 1, 2, 3 here. Here distance between these edges, see you can see that 1, 2, 3, 4, 5. So it must be odd. Since their distance is odd, so they have different colors by the construction of coloring T. Right? Is that fine with everyone? Yeah, say something. Yes or no?
Yes, sir, it's clear.
Okay, fine. Now the converse is very simple. Now converse. So let G be two chromatic. Okay. Now we claim that it has no odd cycle. So claim it has no odd cycle. Why it has no odd cycle? So if it has an even cycle, has an odd cycle, then it needs three colors, at least three colors. Right? Because if you write a odd cycle, for an example, this 3, 4, 5, 6, 7. Oh, this is even cycle. If you write this one, right? So you cannot have a two color because it is one, say 2, 1, 2. Now this is 1 and 2 attached together, so it must have 3. Right? So we are done. That is very simple. Okay. Now that is another there is another one that is also very easy theorem. Now what is it says that a graph is two chromatic if and only if G is bipartite. Okay. So a graph is two chromatic if and only if G is bipartite. Now this proof again very simple. Can you give a quick proof of that one?
So if it's bipartite, then the two independent sets, we can color all the vertices of each of the independent set in the same color, right? So that part is working. And then we've proved earlier that a bipartite graph does not have any, does not have any odd cycles.
No, we don't need that one. So what we'll do? So see this graph is two colorable. So this is the red and say another vertex is blue. Okay. Now what we'll do? We will collect those red colors in one part and blue colors are in another part. So since there is no edges between red and blue, so this is bipartite. Okay. So if it is two chromatic, we collect the red edges and we collect the blue edges and they gives a bipartition. So it is bipartite. And conversely, it is also same. Now, if it is a bipartite, say this is V1 and say this is V2, then colors V1 by red and colors V2 by another color. So you have a two colorable. So we are done. That is a simple proof. Is that fine? So this portion
Yes.
is, so let G is two chromatic with color 1 and 2. Now choose V1 vertices with color 1 and V2 equal to vertices with color 2. Now then G equal then you can say that G is bipartite with the vertex set V1 and V2. So they give a partition. And what about this portion? So let G be bipartite with partition of vertices V1 and V2. Now then color the vertices of V1 by 1 and color the vertices of V2 by 2. So we have two chromatic. So that implies G is two chromatic. Okay, so we are done. That is very simple. Okay, now there is another theorem that's proved again. It is the similar of the first proof. It says that every planar graph is 6 colorable, or you can say that can be colored with 6 colors. Okay. So we have already see one property that if you have any planar graph, then you must have a vertex with at most 5 degrees. Do you remember that?
Yes, sir.
So a planar graph must have a vertex with degree at most 5. Okay. So let V be a such a vertex. That's mean B be a vertex of G such that dV less than equal to 5. Okay, remember that whenever we are saying that can be colored with 6 colors, it means actually at most 6 colors. It means that. So whenever we say that it can be colored with 6 colors, that's mean we are saying that it can be colored with at most 6 colors. So that is the meaning of that. Because if it can be colored with only say you have only one vertex, so it is one colorable. Since it is one colorable, so it is 6 colorable as well. Okay. So anyway, we can say that it is at most 6 colors. So it looks fine. Okay, so this. Now what we will do, we will prove this by induction. Okay, so first remove V. Then G minus V is also a planar graph. So this is G minus V, and this is V. This is 1, 2, 3, 4, 5. Okay. Now say this. Okay. Fine. Now by induction, G minus V can be colored with at most 6 colors. Right? Now what is the degree of V? Degree of V is 5. So therefore one of the 6 color must be missed in the degree in the neighbor of V. So one of those 6 colors is missed in the neighbor of V as degree of V is less than equal to 5. Okay. Now give V the missed color and then G is 6 colorable. Okay. So any question? So note that whenever we are saying that 6 colorable or 6 proper coloring, so that's mean we are not saying that G has at most 6 color. We are saying that G can be colored with at most 6 colors, right? Because if you recall the definition, what is the proper coloring, you can see that what I have defined there. See this, the definition. So let S be a color set of K colors. Now the graph has K proper coloring if there is a function this. We are not saying that this is a surjective function. We are not saying that. Okay. So that's mean if something is 3 proper coloring, so that will be 4 proper coloring as well. That can be 5 proper coloring as well. Is that clear what I am saying? So when we say that K proper coloring, then it is obviously K plus 1 proper coloring as well. It can be K plus 3 proper coloring as well. Because that function may not be surjective. Okay. But when we say that chromatic number, so that's when we are taking that least K. So in that case, if we say that chromatic number and here we have K, that if the vertex set S is K, then that map should be surjective here in this case, in case of chromatic number. If chromatic number is 5 and if you take a color set with 5 colors, then that map will be surjective. But if we say that it is just a proper coloring, then that map may not be surjective. Okay. So in case of here, we have 3 proper coloring. We can say it is four proper coloring. We can say it is 6 proper coloring as well. Okay, but the list number is 3. So therefore chromatic number is 3. Okay, fine. See, if you have any problem, so I don't know, you are not giving any comments or you are not responding anything. So even I do not know it is clear or not. If there is a question, you should ask so that I can discuss that. Otherwise, that lectures also become boring.
It's clear, sir.
Yeah, then you should respond, right? I don't know. No students are responding. Even number of students are very less. Okay, so there is another theorem. It is called 5-color theorem. Now it says that every planar graph can be colored with, we can say that at most, we write at most, to avoid any confusion, at most 5 colors. Okay. Now here is the proof. So let V be a vertex of G such that degree of V is less than equal to 5. Okay. So we can choose such one vertex because we know that if you have any planar graph, then it must have a vertex of degree at most 5. Now we have 2 cases. Case 1. So degree of V is less than equal to 4. Okay. Now this part is very simple. So take now G minus V. Now this is V. Now this is at most 4. Okay. Now by induction, G minus V has proper 5 coloring, right? So but degree of V is less than equal to 4. So thus one color is missed in the neighbor of V. Okay. Now put that color, that missed color, to V. Okay. So then G is 5 colorable.
Sir, which induction you are referring here?
Sorry.
So which induction you are referring here by induction?
Okay. So we assume that this is true for any vertex. We are taking that induction. We are taking induction on the vertex, on the number of vertices of G.
Okay.
Okay. So if you take only one vertex, then it is obviously 5 colorable because you need only one color to color that vertex, right? Now we assume that suppose it has n vertices. Suppose we assume that any graph, any planar graph with n minus 1 vertices is 5 colorable. Now we are doing for G equal to for the G equal Now we are doing for the G where number of vertices is exactly n. Okay. So base case is always whenever we are saying that induction, that's mean we are doing induction on the number of vertices. So if you want, we can miss here, we can write here. So base case is n equal to 1 and G is here 5 colorable because one color is sufficient. Now assume G is 5 colorable where degree vertex set of G that is less than equal to n minus 1. Okay, so now we are doing for the graph G where number of vertices is exactly n. Okay, now this was the case 1 when degree of B less than equal to 4. Now we take the case 2 where degree of V equal to 5. Degree of V equal to 5. Now this is exactly equal to 5. Now what we will do, we have here two cases. First of all, so this is your V. Okay, now say this is V1, V2, V3, V4, V5. See now just concentrate on the proof of this one because that is a tricky one. Okay. So say this is this color, this color, this color, this color, this. So we have 5 different colors, right? Now, what are the possibility if we change the color of V3? Okay. Now these are the 5 colors. Suppose these are the possibility. These are the different 5 colors. Now can you tell me what color we can give for to V? Can we give a color to V?
Remaining V.
No, we cannot, right? Because we have 5 colors and that is the possibility that all the 5 colors are there in the neighborhood of V. So can we give a color to V? Yes or no?
No, sir, not in this current condition. We'll have to change one of the colors of the other.
Right. So we need to change something, right? Now what we'll do? Now we take the subgraph H with color 1 and 3. 1 and 3 means red and green. Okay. Now take this subgraph. Now there are two possibilities. What are the possibility? That V1 and V3 they are connected or they are not connected. Right in that subgraph. Now since we are taking the subgraph with 2 colors, right? Since you are taking the subgraph with 2 colors, then there are only 2 possibilities. Either V1 and V3 are connected or V1 and V3 are not connected. Now we take the first condition. Say V1 and V3 are not connected. Say V1 and V3 are not connected in H. Okay, so therefore we have this kind of So we have this kind of this. So this is blue, green, green, green. Oh, we have red, red. We have this situation. Now what we do in this situation, we can interchange the color red and green. That is possible only in this portion. Okay, so we can do that, right? So we
Yes.
have a subgraph, right? And there are many connected components. So in this component, we are doing interchange the color red and blue, interchange the color red and green. So that's mean now that will be my green, that will be my red, that will be my green, that will be my red, that will be my green, that will be my red. So interchange red and green. One means 1 and 3 to the component containing V1. Now can you tell me what color we can give to V?
The red color.
Here now we can give the color red for red to V. Right? So we are done. So we have a right. We have a 5. We can color G by 5 colors. So we are done. Fine. Is that fine to everyone? Yes.
Yes, sir.
Okay. So now we consider the other possibility. Other possibility means, okay, just the reverse that one. Other possibility means, so in this case, V1 and V3 are connected. Say V1, V3 are connected in H. Okay, so that's mean we have this situation. So that is green, that is red, that is green, that is red. So we have that situation. Okay. Now tell me, can we have, now if we take the subgraph or just I can say that, can we have a, if we take the subgraph of blue and yellow, if we take the subgraph of blue and yellow, so can V2 and V5 is connected? Or forget about blue, or you can say orange. So V2 and V4, are they connected? Are they connected by blue and orange?
No, sir, they can't.
Why?
Sir, because like in this case, if we had just considered the subgraph, right, in red and green, right, we can observe that if V is a point in the subgraph, it can't be a point in the subgraph because then we'll have an odd cycle. So if we choose the other two colors, right, any other two colors, if they are also connected, then there will V will not be, there will remain no color for V because it is connected to the third color that is left, right? So we can't point at that color also. And in the case that you said V2, V4 are connected, so we can't appoint blue or orange also. So then we won't be able to color.
Right. Now, what actually the question is, what I have asked that, if you choose the color blue, and if we choose the subgraph here blue and orange, so can V2 and V4 can be connected by the color blue and orange? It is no. Why? Can you tell me what will be the color of V in this case?
It would have to be yellow.
No. In this case, no. We are saying that in this case, if we take that color V2 and V4, then we have to come via in this way. So this is the only possibility, right? If we want to connect V2 and V4, then that will not be a planar graph. That is the main question.
Okay.
Right? Because if you have to this, then we should have this kind of cycle.
Yes, sir. Got it. Sorry.
Right? Because actually what is by drawing, what is our V2? You can see that. You can
Sir,
see
I
that
don't
this
get
one,
this.
you can see that V, you can see that V1 and this one actually. So this one forms a cycle. Right? So this one forms a cycle. Now if we remove that cycle, then V2 will be inside of that cycle and V4 is outside of that cycle. Okay? So there will be no other path from V2 to V4. There is no other path from V2 to V4. Did you get what I'm saying? Because otherwise it should intersect. Since it is a planar graph, so that is not possible. Okay, so
Sir, we
huh.
sir we can join B2 and B4 using a vertex at B3.
Using the vertex set no, V3 is not possible, right? Because V3 has already this colored. We are talking about in H. H means now, okay. Now we are talking about say not H. We can now taking K be a subgraph with color blue and orange. Okay. So V1, V2 that will not be there.
Okay, sir.
Okay. So we are talking about only the subgraph with blue and orange.
So
Okay.
why can't we connect this B2 and B4? We can have a cycle like the similar to one that we have in B1 and B3.
Right. So if you have a cycle, then that cycle should cut somewhere. But this is a planar graph, right? So that is not possible. That
Yes.
self intersection is not possible. Intersecting of edges.
But like we can make B2 to the left of B1 and then we can join B2 and B4 from this other side, not from the side where we have cycle, from the other side.
Right. So that is the reason at the first we choose that we choose the direction fixed, and then we do this one. So we choose V and then V1, V2. We just rename V1, V2, V3, V4, V5 in clockwise, and that direction is fixed. Okay. So at the beginning we will do that. So that direction is fixed. So V1, V2, V3, V4, V5 in a clockwise. Okay. So this cycle is not possible since this is a planar graph. So therefore, if you take the subgraph K with color blue and orange, then V2 and V4 must be in a different component, not same component. And then we can interchange the color V2 by the similar approach which we did last time. So we are done. So this is the trick for this proof only. Okay. So I can show you. Yeah. So that was actually the case. So if you already have V1 and V3, if they are connected by a cycle, okay, then you cannot have any cycle from V2 to V4, because otherwise you have to intersect somewhere. Since this is a planar graph, so that is not possible. So therefore you cannot have another cycle with V2 and V4 and with V. So you cannot have any cycle, because if there is another one path from V2 to V4, then you must have this kind of path. And with V4, V2 and other vertices should be a cycle. Then we will have a two cycle with self intersecting. But that is not possible because this is a planar graph. So this condition is now is not valid. So therefore, if you in this case, if you take the color of the component with yellow and red, then this should be, then V2 and V4 should be in a different component. And then we can do the, we can just replace the color red and yellow for the component containing V2 and then put the color red to V. So we are done. Okay. So we will do the previous case, this one. See, if V1 and V2 lies in a different component of H, okay, then we can just take this, we can just consider the component of H containing V1 and we can interchange the color. Okay, so what we do, we can do the case 2A again here in this case. Okay. So if V1 and V3 are not connected, then we did A5 coloring, right? Now if V1 and V3 are connected, then we prove that V2 and V4 are not connected. And since V2 and V4 are not connected, then we can do the similar approach which we did just before that one. That's mean we can interchange the color blue and orange in the component containing V2, and then that V2, this color will be changed to orange, and then we can put blue to V. So we are done. Okay. Okay, so any doubt? So anyway, you can read. I think that will be clear. So when you go through the lecture notes. Okay, now there is another theorem. Now what we proved? We proved that any planar graph can be proved with at most 6 colors. Any planar graph can be proved with at most 5 colors. Now there is another one, that is 4 color theorem. So any planar graph can be proved, can be colored with at most 4 colors. Okay. Now the proof is very long and by using computer. So there is no theoretical proof for that one. So therefore we will not prove that. Okay. So we can stop today. So if you have any question, you can ask. Yes, do you have any question?
No, sir.
Okay. Okay. Then we can stop today.